Hello folks, today we'll talk about the span of a collection of vectors, material from 1.3. So recall that the idea here is that if we have a collection of vectors, say v1, v2 through k, if this is a collection of vectors, let's say these are all in Rn, so each one has n entries, the span, we call this set S. The span of S is the set of all possible linear combinations. So in other words, so more precisely, everything that I can write as C1v1 plus C2v2 plus up through CKvk, every possible linear combination that I can write among those vectors is an infinite collection. It's the span. Okay, so just some things to note here is that note that the zero vector is always in the span of S, the span of this collection, because I can always write, this comes down to the fact that we can always solve the homogeneous equation, but I can always write 0 as 0v1 plus 0v2 plus, 0vk. So the zero vector is always in the span. Another thing to realize is that each individual vector is also in the span. So each vi, let's say, is in the span of this collection. And why is that? Well, because I can always write, if you want vi, what I'm going to do is write this as, I'll take 0v1 plus 0v2. I'll write everything as a zero weight, except until I get to this vi, and I'll just take 1 times it, if you like, 1 times it, and then plus all the zeros of everything else. So everything gets a weight of 0 except this vi. It gets a weight of 1, and therefore, of course, that equals vi, therefore vi is in the span. Okay, so that's the idea behind a span. And let me just recall that to decide if a given vector, say b, is in the span of v1 through vk, what we do is we solve a what's called the vector equation, right? We solve the vector equation. To decide if a vector b is in the span of that, I need to say, can I write b as something times v1 plus something times v2 plus something times vk, right? So this is called the vector equation, which means I have to solve, right? Remember, to solve the vector equation, I actually look at the system where I take v1, v2 as the columns up through vk, and then I augment with b. Okay, so those are the kind of most important facts about span. Let me just do maybe a couple examples here. So we might have seen this example before, but just to go back to it. So for instance, if I take the span of, let's take 1, 2, 0, and 3, minus 1, 1. So these are vectors in R3. And, let me draw kind of a cartoon here. So here's R3. I've got 3 coordinate axes. And, these vectors are, so what is this? This is 1, 2, 0. So the vector v, this is, say, v1. Say this is v2. So v2 is 3, 1, 2, 3, minus 1, and then up 1. So it's something like this. And the span will be all possible linear combinations. So I can take v1 plus v2. I can take v1 minus v2. I can take 5v1 minus v2. I can just take 6v1. But we saw this before, that what we're going to get is a plane. This will be the span of v1, v2. Okay? Now, we saw this before, that assuming that these are two vectors in R3 that are not a scalar multiple of one another, you'll always get this plane through the origin, right? It's going to be the plane that these two vectors, you can think about, these two vectors sticking out of the origin, they define this infinite plane, this kind of all the vectors that sit in that plane. So, all these vectors here that sit in this plane, So for instance, V1, say, plus V2 would be something like this. This would be something like V1 plus V2. I could also take 2V1, and then 2V1 plus V2 would be something like this. I could take minus V1, right? It's an infinite collection. I'm not gonna be able to draw this, but all those vectors I get as linear combinations. All of these things of the form C1, 1, 2, 0, plus C2, 3, minus 1, 1. You can choose anything you want for these weights, and you'll get a vector that's in the span. Okay. Now, what if I asked you is, I don't know, the vector, let's say 2, 1, 3, is this in the span? Is this in the span of those two vectors above? And again, what this is asking is, can I write 2, 1, 3 as something times 1, 2, 0 plus something times 3 minus 1, 1? So it's sort of a question. Can I find those weights? Right? That's the same thing as asking, is it in the span, is saying, can I write this vector as a linear combination? So what does this mean? I want to solve this vector equation, which means I take, right, those vectors as the coefficient matrix, and then I augment with 2, 1, 3. And then what you want to do is, what I'm asking now is there a solution to this, right? So what I should have said is, does the equation, the vector equation, have a solution? That's what I'm really asking here. And so that's the same thing as saying, does this, same thing as asking, does this system have a solution? Let's reduce this thing, so I'll clear it below that pivot there. So this will be 0, and then let's see, minus 2. This will be minus 7, minus 3, 0, 1, 3. And then let's see, so, well, maybe I'll swap that first, the second and third row. I know this thing's going to be inconsistent, but let's just go through the motion here. So when I now clear below that pivot, what I see is it's 1, 3, 2, 0, 1, 3, and then 0, 0. I'm taking 7 times that, so I think that's 18. Is that right? 7, 21. Yeah. So what you see here is that there's a problem, right? That's an inconsistency. So this implies that the system is not consistent, which tells me that this vector 2, 1, 3 is not in the span of, well, what we called V1, V2. Okay. Okay, one more example I want to present here is this issue of, or this notion of spanning all of Rn, right? So let me maybe consider something else here. So let's take this example, I don't know, let's take 1, 2, 2, 4, and I don't know, 1, minus 3. So these are vectors in R2 now. I can draw these, right? These are vectors in R2. Let's draw them. Let's see, so 1, 2 is this guy. 2, 4 is actually this thing, right? It's a multiple of that. And then 1 minus 3 is down here. Okay, so those are those three vectors. Notice that one of them is actually on the line determined by another. And I want to know what's the span of this set. So if this is S, let's describe the span of S. What are all possible linear combinations? So again, what I'm looking for is everything I can get by taking a linear combination of these three vectors. So all vectors that look like that. Well, notice now, so I'm going to take a slightly different perspective. Suppose we take any vector, just an arbitrary vector in R2. So what if I just take any old vector, let's say this guy here. Here's B. It's B1, B2. Can I write it as a linear combination? So I want to now ask, is B in the span of S? Okay. Well, as before, what we're going to do is we're going to solve a system that looks like 1, 2, 2, 4, 1, minus 3. Augment now with the B vector, which I now know is B1, B2, right? But notice what happens now. So now when I row reduce, this thing will be my pivot. 1, 2, 1, B1. I'm taking minus 2 times that first row added to the third. So this is now, what, minus 5. And this is B2 minus 2B1. Okay. But notice I can stop here, because what I see is that there's a pivot here and a pivot here. There's a pivot in every row. So now I know that no matter what B1 and B2 were, this will be consistent, right? There's no problem with my rows having this, this row of zeros, which would make it inconsistent. So what I know now is that the system is consistent no matter what, for all vectors B. No matter what B was, if I put it on the right-hand side as an augmented matrix, I get a consistent system. So what this is telling me is that every vector, no matter which vector you give me, everything that has 2 coordinates is in the span of these 3 vectors. No matter which vector you give me, there's going to be some way to construct it as a linear combination of what you gave me here. Okay, and so, for instance, well, I won't try to do it here, but we can write this vector as taking, some negative part of this vector plus some negative part of this vector, and if you, choose your weights correctly, you'll be able to actually describe B as a linear combination. So every vector B is in the span. What we say then is that the set S spans all of R2. Okay? And in general, right? So in general, if A is a matrix, is an m by n matrix, and has a pivot in every row, then the columns of that matrix span, well, it spans everything. And what is it going to be? Well, remember we have m rows, which means that each vector that I'm looking at has m entries. So what I know is that every vector with m entries will be in the span. In other words, the span will be Rm. Okay, and so that's the kind of general fact we might have seen before, but just to kind of put it into context here. Okay, so that's the kind of review of span. Hopefully that helps. We'll see you next time.